Elon Musk stated that Starship will be sent to Mars by the end of 2026 and that manned missions could begin in 2029. However, today, a question casts a long shadow over this dream. Is sustainable space travel nearly impossible? Let's start with the numbers. In 2024, NASA reported that even with reusable rockets, the cost of launching just 1 kilogram of cargo into low Earth orbit is still approximately $1,500. To reach Mars, multiply that figure by nearly 100. The energy required to escape Earth's gravity, approximately 9.4 kilometers per second delta V, means we need to burn enormous amounts of fuel just to leave our planet. Each launch emits hundreds of tons of carbon dioxide and aluminum oxide, which damage the ozone layer. If we continue at the current launch rate, approximately 230 orbital launches per year by 2025, the environmental footprint will reach a level that rivals small industrial sectors on Earth. Therefore, as our rockets become cheaper and more reliable, sustainability becomes more important than ever. Can we build a system that allows us to explore the cosmos without destroying the environment that gave birth to us? To find the answer, we must first challenge a common belief. If we improve our technology a little more, sustainable and continuous space travel will become possible. At first glance, sustainability in space travel sounds simple. Make rockets reusable, switch to green fuels, improve efficiency. But in reality, physics has no sympathy for optimism. The Tsiolkovsky rocket equation tells us that the amount of propellant needed grows exponentially with velocity. To reach Mars sustainably, we'd need propulsion systems capable of tens of kilometers per second of exhaust velocity, something current chemical rockets can't deliver. Even SpaceX's Raptor engines, the most advanced methane-oxygen engines today, achieve only about 3.5 kilometers per second exhaust velocity. Nuclear thermal propulsion, tested by NASA under the Draco project, might reach 9 kilometers per second, still insufficient for deep space travel at sustainable fuel ratios. The energy cost is extremely high. Accelerating a 100-ton spacecraft to a speed of 10 kilometers per second requires approximately 5 trillion joules of energy. This is equivalent to the total daily energy consumption of approximately 4,000 American households. Maintaining this rate for interplanetary travel would mean an unsustainable demand for energy back on Earth. And propulsion isn't our only obstacle. Cosmic radiation exposure, microgravity-induced muscle loss, and the sheer logistical nightmare of recycling air, water, and waste in a closed-loop system push sustainability to its limits. Even the most efficient life support systems, like the ISS's Environmental Control and Life Support System, can only recycle about 93% of water and 75% of oxygen, meaning every long-term journey still requires resupply from Earth. So maybe, just maybe, sustainable space travel, as in travel that can continue indefinitely without harming Earth or exhausting resources, is fundamentally constrained by physics, not technology. Now you might be wondering, if the data is this discouraging, why believe in a counter-approach at all? Why trust the idea that sustainability in space might still be possible? Because history shows that humanity thrives on breaking constraints once thought unbreakable. 50 years ago, sending even a single satellite to orbit cost $50,000 per kilogram. Today, thanks to reusability, modular design, and miniaturization, that number has dropped by more than 95%. Solar panel efficiency doubled between 2010 and 2025. Batteries became 4 times more energy dense. Each technological revolution compresses what was once impossible into the realm of reality. But optimism alone doesn't build rockets. The reason to trust this opposing view, the belief that sustainability isn't entirely out of reach, lies in the data. Emerging propulsion systems such as ion drives, solar sails, and fusion-based engines are redefining what fuel efficiency even means. Take the NASA Dawn mission, powered by ion propulsion. It achieved a total delta V of 11 kilometers per second, using just 425 kilograms of xenon fuel, something no chemical rocket could ever do. The upcoming Helicity space project aims to use magnetized plasma fusion propulsion, potentially achieving exhaust velocities exceeding 100 kilometers per second while using deuterium, an isotope that can be extracted from seawater. These breakthroughs hint that sustainability isn't about reducing fuel, but about changing the rules of how energy is used in space. Here's the part most people miss. The real breakthrough in sustainable space travel isn't about rockets at all. It's about energy ecosystems. In 2023, the European Space Agency began testing orbital solar power satellites, massive panels that collect sunlight in space and beam it back to Earth via microwaves. Theoretically, this same system could power interplanetary infrastructure without carrying fuel. If even 1% of Earth's orbital area were covered with these collectors, it could generate enough power to sustain every launch on Earth cleanly. Similarly, NASA's Kilopower reactor project demonstrated compact nuclear reactors capable of providing 10 kilowatts of continuous power for lunar and Martian bases. Combine that with electrolysis-based fuel generation, and we could literally create rocket propellant from Martian ice, turning water into hydrogen and oxygen on demand. Recent simulations from MIT suggest that an optimized closed-loop life support system combined with solar and nuclear hybrid energy could achieve 97% material recycling efficiency, a number that edges close to true sustainability. So while our rockets themselves may never be green, the infrastructure around them could be. The key insight is this: sustainability in space travel won't come from lighter engines, but from smarter ecosystems that recycle, regenerate, and reuse. If this new approach succeeds, what would it mean for humanity? Let's start with the benefits. By developing sustainable systems in space, we could shift high-energy industries off Earth. Mining asteroids for platinum group metals, for example, could meet centuries of demand without touching Earth's crust. Space-based manufacturing could eliminate atmospheric pollution entirely. Colonies powered by closed-loop systems could operate for decades with minimal resupply, becoming truly self-sustaining. The scientific payoff would be enormous. Permanent research bases on Mars, exploration of Europa's icy oceans, and even interstellar precursor missions within a century. The psychological impact, knowing we can live beyond our cradle sustainably, would redefine what it means to be human. But there are dangers, too. Sustainability in space could create economic divides, with wealthy nations monopolizing orbital infrastructure. The environmental benefits could turn into political weapons. Who controls the clean energy of space? And as space becomes accessible, so too does the potential for orbital debris and energy misuse. Still, the alternative, giving up on sustainable space travel, means accepting that our destiny ends at the edge of Earth's gravity. Yet the story doesn't end with building habitats or mining asteroids. In 2025, NASA's Jet Propulsion Laboratory published projections suggesting that a fully self-sustaining Mars transport network would require at least 500 tons of annual payload capacity between Earth and Mars. That's roughly 10 times the total mass ever delivered to the Martian surface since the beginning of space exploration. Achieving this requires a complete overhaul of propulsion and energy logistics. One of the most promising developments is beamed propulsion. Using ground or orbit-based laser arrays, spacecraft could receive thrust from photon pressure or via heating a propellant. A 2024 MIT Caltech study showed that a 100-megawatt laser array could accelerate a 1,000-kilogram probe to 20 kilometers per second within minutes, no onboard fuel needed. Scaling this system up could reduce launch costs by up to 90% and remove the need for massive onboard tanks, one of the main sustainability bottlenecks. Meanwhile, electrodynamic tethers, long conductive cables using Earth's magnetic field, have already demonstrated the ability to deorbit satellites without fuel. ESA's 2023 ET-PAC mission proved that a 2-kilometer tether could generate 0.4 newtons of continuous thrust, enough to alter orbital trajectories over weeks. Imagine networks of such tethers on Mars or in orbit, constantly recycling spacecraft between worlds using nothing but magnetism. But propulsion is only one half of the equation. For long-term missions, the real challenge is material sustainability, how to build, repair, and reproduce complex systems without supply chains from Earth. Here's where in-situ resource utilization, ISRU, becomes the cornerstone of interplanetary sustainability. According to a 2025 NASA ISRU roadmap, extracting just 1 cubic meter of Martian regolith can yield 60% oxygen, 17% iron, 15% silicone, and 5% aluminum by mass after processing. With this, 3D printed alloys can replace Earth-manufactured components. In experiments conducted at the University of Colorado Boulder, simulated Martian dust was successfully used to print structural beams capable of withstanding 20 megapascals of compressive strength, nearly equivalent to terrestrial concrete. Add biopolymer synthesis to this so that even food and living space materials can be produced locally. Energy production continues to advance. Despite all the negativity we mentioned in our initial statements, we are gradually laying the foundations for a civilization that can live and thrive beyond Earth. So when we ask again, is sustainable space travel nearly impossible? The numbers show that it is not impossible. The answer is simply not yet complete.